Hello, this video is about lenses, and it probably will make a little more sense if you go and watch the video on curved mirrors first. But if you haven't, you still should be able to make sense of this. So lenses are usually glass, and we often have them shaped like this. So let's think about what's happening if we take a big piece of glass and shape it like this. Okay, that's terrible. Doom. Okay, there we go. That's a little better. We can have light rays that come from over here, go from the air into the glass, and then back into the air. Now, when we change media, when we change from one material to another material, that's refraction. So we can use our ideas about refraction to figure out what happens with lenses. Let's say we have light rays coming in to a big old lens. What's going to happen to those light rays when they hit the glass? So let's take this one. All right, we hit the glass. It's at an angle like this. Now for refraction, remember that we have to figure out everything relative to the normal, which is perpendicular to the surface. So the surface is like this, which means the normal is like this. All right? And we're going from air into glass. We're going into a more dense material, which means we bend towards the normal. So if there was no transition, the light ray would continue to go like this, but we're bending into something more dense, bend towards the normal. So we're going to bend down like this. Okay, so now we've got the light ray going through the glass at that kind of angle. What's going to happen to it when it hits the next transition? Okay, here's our next transition, and my normal would be perpendicular. Now we're going from glass into air. Glass into air, we're going into a less dense material, less optically dense material, and so we bend away from the normal. The light ray normally would do this, but we're going to bend away from the normal. There's my normal, we're going to bend away from it. So we're going to bend downwards. Okay, so that's an example of what one of the light rays will do when it hits this lens. Let's do another one. How about this one? Okay, same idea. Here is my surface combination. My normal would look like this, going into a more dense material, and so I'm going to bend towards the normal. So I'm going to bend up a little bit. And now here's my new surface. So my new normal would be something like this. I'm going from glass into air, something from high optical density to low optical density, which means we bend towards the normal. So we'd come in like this, but we'd bend towards the normal a little bit. All right. And then if we've got something kind of in the middle, I'm just going to pretend there's the middle. And if we're exactly perpendicular, which is my picture is not, sorry, then exactly perpendicular, there's no bending. But what we would have is a light ray that goes straight on through. So just as we saw with curved mirrors, a lens can take parallel light coming in, and all those parallel rays will converge down to this point. And we call that our focal point again. So there's our focal point right there, where all those parallel light rays meet. So just like with curved mirrors, kind of the definition of a lens is that it has a focal, and that focal is dependent on the curvature. If we have a really curvy lens, the focal is probably going to be pretty close in, maybe even like that close. If we have a really flat lens, the focus is going to be way out here. Now the interesting thing with lenses compared to mirrors is that I can have parallel light coming in this way. It all gets converged down to this focal point. I could flip this whole thing over if I have parallel light coming in this way, and it all gets converged down over here. So for lenses, we actually have two focal points, one on each side, because the light rays are it would be symmetrical. Parallel light in, choop, meets here, parallel light in meets here. And so for lenses, we have two focals, one on each side, equal distance. All right, so how do lenses make images? Well, if you have glasses, you know that curved lenses, like this, yep, they make images, and they're doing something to what we typically have. You know, if I do this, I'm seeing different things than if I do this. So how do curved lenses actually create images? Let's do that. And this is not erasing very well. Okay, so let's get it set up just like we set it up with curved mirrors, but now with lenses, instead of the light bouncing off the mirror, we are going to have light going through the lens, but it's getting bent when it hits the lens. So let's see what we can do with this. Let's say we have a lens, and I'm going to do that horizontal axis, and now I've got a focal on both sides, equidistant, and let's put an object out here and see what happens to those light rays. So we saw all the parallel light rays that came into the lens, they all got converged down to the focal, and then it's just going to keep on going. So one of the light rays is going to come in parallel, go through the focal. And remember, if this is something, a source of light, or even like me, light's hitting me and then it's bouncing off in all directions, so we can draw as many light rays as we want, leaving this object. We also, the kind of inverse, the opposite version of the focal length, if there is a light ray that comes in through the focal length, it turns out it leaves the lens parallel. It's one of the cool things about the focal is that it's got this inverse relationship. Parallel in, out through the focal. In through the focal, out parallel. And with curved mirrors, we could either say it hits the center of the mirror and bounces off at equal angles, but then you have to have like a protractor to do it really well. So what I did was I said the center of curvature is twice the focal. So if my focal length is here, center curvature is here. And then a light ray that goes through the center curvature bounces off on itself. We can have something similar with this, but what we're going to do is we're going to go through the center of the lens. So if we have a light ray that goes through the center of the lens, it just keeps on going. It doesn't get bent at all. All right, what does this mean? Those light rays are meeting up somewhere. So where those light rays meet up, we have an image formed. So our object is here, and we have an image formed here. What do we know about that image? Well, okay, this was above the axis, this is below the axis. So if my object was a person, that means they are upside down. So we have an inverted image, and it looks like it's a little bit bigger. The image here for this kind of situation, it could be bigger or smaller, but just like with curved mirrors, this could be a real image. This is a real image because the light rays actually leave the object. They get bent by the lens. Those light rays actually meet up here. If you put a screen here, a piece of paper here, you would see that image. Okay, so we have a real image. It's inverted, and depending upon how far away you are, it could be bigger or smaller. So in this case, it looks like it's a bit bigger. So I had that height, and yep, it's bigger. Okay, so that's my first situation. Now let's see if we can figure out the second situation. If you've seen the mirrors video, see if you can figure out what the rays are going to look like for an object really close to the mirror. So that's our next situation. What if we have an object really close to the mirror? Okay, there we go. So I'm going to create, oh, I said mirror. I'm sorry. I meant lens. I get them confused. I just did the video on mirrors, and so I'm thinking about mirrors. Let's do this again. So lens, that's what I mean. Here's my horizontal axis. We've got focal points. Ooh, I'm going to make the focal actually farther out. Okay, shoop, shoop. Focal. So now if we have an object that is close to the lens, within its focal point, let's say it's here. What are those light rays going to do? All right, so we have the parallel light rays that go in. They all converge to the focal point. So that's one of my light rays. I also have a light ray that goes straight through the center point, and that doesn't get bent at all. It just goes whoop, and keeps on going. My third light ray, back when we had something far away, we had a light ray from the object through the focal to the lens. So here we're just kind of reversing the order. We're going to still line up the object and the focal, but it turns out the focal is first. So if we have a light ray that lines up with the focal, so we've got a light ray that's lining up, object and focal are lined up, it's going to leave the lens parallel to the axis. Okay, where do these three meet up? Well, they don't. They don't. They are spreading out. And so these will never converge in actuality. There is no place you could put a screen over here or a piece of paper or whatever and actually see an image. But just like with curved mirrors, we can trick our eye into thinking that an image is formed back here. So if we trace these rays back, whoop, this is going to be messy. I think I have a ruler here, but hey. Something like that. So if I trace these three rays backwards, yeah, messy. If you do this on paper, hopefully it works a lot better. Right here is where my image is formed. So this was my object. If I have an object close to the lens, then we don't actually form a real image. Light rays can never converge over here, but our eye can get fooled into thinking that there is an image formed here. So if your eye is here, you don't see the object. What you're going to see is an image of that object, and it is upright and magnified. This is a magnifying glass. So if we are close to this kind of lens, we have something that is upright and bigger. And this is a virtual image because those light rays do not actually meet up. But your eye says, it follows these and says, oh, all these trace back to this point. The object must be there. All right, one more type. One more type. What would that type be? With lenses, I'm getting these mixed up. With mirrors, what did we have? We changed the shape of the mirror. And just the same thing here, we can change the shape of the lens. So now, instead of a lens that's skinny at the edges and thicker in the middle, we are going to have the reverse. We're going to take a lens that is skinny in the middle and thicker at the edges. And let's see what that is going to do to light coming in. So if we have this shape of lens, all right, so we've got parallel light rays that come in. What happens to those parallel light rays? Okay, this one, it's hitting at like this angle, so my normal would be like that. It wants to come in like this, but it's going into a more optically dense material. It bends towards the normal. So this is going to bend like that. And now we're hitting like this. I have a new normal like this. We're going into a less optically dense, and what happens into less optically dense, we bend away from the normal. Whoosh! That one's going through. This one's going straight. Same thing here. We bend towards the normal, and then We bend away from the normal. So with this shape of lens, parallel light rays coming in get spread out. So we call this a diverging lens. This is because it takes those light rays and spreads them out. It diverges them. Excuse me. So what is this going to do? Can we create an image with a diverging lens? Well, yeah. I have, I don't know if you can see, but my lenses, the lenses of my glasses are skinny in the middle and thicker on the edges. My glasses have diverging lenses. What do they do to create an image that I can see? Let's give it a try. And we're actually going to use similar rays. We just have to figure out what those rays are going to do. So if we have a diverging lens, and here's my horizontal axis. Now, does this have a focal point? I shouldn't have erased it. Does this have a focal point? All those light rays, that parallel light rays came in and they'd spread out. As with a convex mirror, this diverging lens has a virtual virtual focal point. It's not a real focal point because the light rays don't come in and get converged down. You can't put a piece of paper or something there and see all the light come down. They get spread out, but we can trace them backwards to a virtual focal point. So light rays coming in this way get spread out, we trace them back to here. If we have light rays coming in this way, they get spread out, we trace them back over here. So we still have the two focal points, but they're virtual focal points. And if we do the math, what we do to tell ourselves that it's a virtual focal point is we say this is a negative focal. So let's put an object out here and see what those light rays do. All right, so if we have a light ray coming in parallel, then the diverging lens spreads those rays out. How's it going to do this? It's going to line up with this focal right here. And so we have that spreading out. We've got a light ray that goes through the center of the lens. Oh, yeah, well, I'm not a great drawer. What's our third light ray? We've used this focal. We've used the center of the lens. We still need to use this focal. This is a sneaky one. If we have a light ray that aims at that focal, so it's aiming at that focal, but as soon as it hits the lens, it's got to do something different. If we're aiming at the focal, we're going to go out parallel. And so the third ray, if we aim at that farther focal, it leaves parallel. So here, 1, 2, these three rays are leaving the lens. They don't meet up over here. We do not have a real image because these three rays never meet up on this side. But if we put our eye here, our eye gets fooled into thinking that they all converge around here. And that is what happens. So if we trace this one backwards, done. Trace this one back on itself, done. Trace this one back, what we get is an image formed right there. So here's our image, here's our object. And what do we see? Oh, okay, it's upright. This is above the axis. This is above the axis. And our image is much smaller, much smaller. So here we have a virtual image because the light rays don't actually meet up. We have to imagine that they do. It is upright and it is smaller. So to summarize lenses, if we have a converging lens and we are far away, what we get is an inverted upside down image. It could be bigger or smaller than the actual object, and it is a real image. We can put a piece of paper there, put a screen there, and see it. If we're really close to a converging lens, if we're within that focal point is the key, then we have an upright image, and it is big, and it is virtual. The light rays don't actually meet there. You can never see a virtual image on a piece of paper. You can only see with your eyes. The third type of image we can have is a diverging lens, and we can be anywhere, it doesn't matter, anywhere in front of a diverging lens. We get an upright image. It is smaller, in this case much smaller, and it is also virtual. The light rays don't truly meet there. We get tricked into imagining that the image is here, that the light rays are coming from there. So there is a summary for converging and diverging lenses. Good job for watching.